So since Bohr's model was a failure, people began to look for a new model of the atom, which focused on the newly found wave properties of electrons. And so this new quantum mechanical model modeled the electrons as standing waves. So instead of going around the nucleus in circles, as in the Bohr model, you can see here they go around in kind of squiggly lines, which are waves. So it turns out there's a fundamental limit to how accurately we can know both the position and momentum of a particle at any time. And this actually applies to any particle. But for big objects such as a ball, then the uncertainty is pretty small. But when we get to really small particles like electrons, then the uncertainty is quite big. So this is called the Heisenberg Uncertainty principle. So although we can't know the exact motion of an electron or its exact position, we can calculate the probability of it being in a certain position. So, for example, when we think of planets' orbits, we think of them going around the sun in an ellipse. And we know that the planet follows this ellipse almost exactly. However, since we can't exactly know the position of an electron, we kind of have these big blobs where we can probably know that the electron is moving around somewhere inside this big blob. And so these blobs, or regions of space in which the electrons are probably moving around in, are called an atomic orbital. And each atom can have multiple atomic orbitals. And so we can describe each orbital in an atom with a series of quantum numbers. They're basically like the address of an orbital. So the first one, the principal quantum number, n, describes the size and energy of an orbital. So the larger the value of n, the larger the orbital and the higher energy the orbital is. Because the further out from the nucleus the orbital is, and therefore the electrons, the more energy it takes to keep them attracted to the nucleus and not like fly off. And so in higher energy orbitals, the electrons on average spend more time further away from the nucleus. Remember that we don't actually know where they are exactly. We can only talk about the probability of an electron being in a certain place. And so the principal quantum number has integer values starting from 1, and it just keeps going 1, 2, 3, etc. Next we have the angular momentum quantum number, L, which describes the shape of the orbital. And this has integer values from 0 to n minus 1. So for example, if n was 4, then L could be 0, 1, and 2, and 3. And we usually assign this quantum number a letter. So 0 is S, 1 is P, 2 is D, and 3 is F. We don't use the ones higher than this. So the last one for orbitals is the magnetic quantum number, ML, which describes the orientation of the orbital in space. And this one has integer values from negative L to L, and it includes 0. So each set of orbitals with a certain value of L under the same principal quantum number is called a subshell. And we denote a subshell with the n and the letter assigned to the value of L. So here we have a big chart. So just as an example, when n is 3, then L can be 0, 1, or 2. So within the third principal quantum level, there are 3 subshells: 3s, 3p, and 3d. Now, each s subshell, no matter what principal quantum level it's in, will only have one value of the ml, 0. So, since there's only one value of ml, there's only one orbital. The 3p, or any p, subshell will have 3 values of ml, and therefore 3 orbitals. These subshells have 5 values of ml and 5 orbitals. So the fourth quantum level and beyond is when we start having the f subshell, which corresponds to the value of 3 for L. And each f subshell has 7 values of ml and therefore 7 orbitals. So remember, these 3 quantum numbers, n, l, and ml, describe an orbital. If we want to describe an electron inside that orbital, we need a fourth quantum number. And this is due to the electrons spinning, so they can spin in either one of 2 directions. And so we have a fourth quantum number, the electron spin number, ms, which can only be either positive or negative 1/2. So for example, if we wanted to describe an electron in the 2s subshell, then n would be 2, L would be 0, because 0 corresponds to s. So n is 2, L is 0. Now we're in the 2s subshell. And then there's only one value of ml, which is 0. And then the spin number could be either positive or negative 1/2. So the Pauli exclusion principle says that in any atom, no 2 electrons can have the same 4 quantum numbers. So since there are only 2 possible spin values, this means that each orbital can only hold 2 electrons. And these 2 electrons must have opposite spins. So the s subshells have 1 orbital, which means they can have 2 electrons total. P orbitals, or p subshells, have 3 orbitals and 6 electrons. D subshells have 5 orbitals for a maximum of 10 electrons. And therefore f subshells have 7 orbitals and can hold 14 electrons. So far we've only been talking about the hydrogen atom, which only has 1 electron. But as you know, most elements have more than 1 electron. So when more than 1 electron are present in an atom, it creates a bunch of repulsions because all the electrons simultaneously repel each other. So this repulsions between the electrons weakens the attraction between each electron and the nucleus. So as you add more electrons, then the attractive force between the nucleus and each individual electron gets weaker. So this is known as the shielding effect. So basically the extra electrons shield the individual electrons from the nuclear attraction. And it increases as the number of electrons between the nucleus and an electron increases. So if there are a lot of electrons, for example, if the electron we're looking at is in one of the higher principal levels, and therefore further away from the nucleus, there are more electrons in between it and the nucleus, so it's shielded from the nuclear attraction to a greater extent. So also in atoms with more than 1 electron, the subshells within a principal level differ in energy level. In the hydrogen atom, each all of the subshells within a given value of n are actually at the same energy. They're said to be degenerate. However, this is not the case in most elements. So it turns out that the S subshells have the lowest energy, and then it increases from P to D to F, so that F has the greatest energy. So since electrons like to be at low energy, when put in a given principal level, they prefer S, then P, then D, and then lastly F.